Okay, here's video to accompany the lesson 14.1 in the pre-calculus textbook. I hope you've already done the reading, reading and done the guided reading sheet and took your notes in your notebook. The purpose of this video is try to make a little bit more sense about what you read and see if you can hopefully better understand it before you start the homework exercises. So this lesson really gets to three things, and the three main ideas in the lesson are to understand how to properly express statements using limit notation. We did get a little bit of exposure to this in pre-calculus this past year using the proper limit notation. Secondly, to understand the informal definition of limit, and that's quite a long definition that you've written in your notebook, but to fully understand it would be real important. And to know when the limit of a function exists and when it doesn't exist. The big idea here is to understand that when it comes to limit, we're not concerned about what happens, how a function's behaving at a particular value of x, but instead we're curious about and we study how the function is behaving as we get closer and closer, very near an x value, a particular x value. Now sometimes limits are actually equal to the value of the function at a point. For example, the function f of x equals x squared. We know it's a continuous function, it's a parabola, and as we say we want to look at the limit as x approaches 2. Well, we know that let's just take a visual of this for a moment. Whoops. If we look at the function f of x equals x squared, and then take a quick look at a rough graph here. It's a parabola that has a vertex at the origin, and if we look at the point 1, 2, right here, we know from substituting 2 into the rule that this is the point 2, 4. And really, the notion of limit would be, if we're asking ourselves this question, what is the limit of f of x as x approaches 2? What we'd be asking ourselves is, as we look at this curve right here in this vicinity, as we get closer and closer to the x value of 2 from the left side and from the right side, does it appear that we're getting closer and closer to a particular value? Does it look like the function's value is getting to be closer to a particular finite value? And I think we'd all agree that it is. It's getting closer and closer to 4. The closer I get to 2 from here, I'm getting closer to 4. The closer I get to 2 from the right side, I'm getting closer and closer to 4. So that's what we mean by the limit. Sometimes the function's limit is actually equal to the value there. Sometimes it's not. So here is our informal definition. And there are really two parts to this definition. There's this part here which basically says that if you can take values closer and closer to, but not necessarily equal to c, if the function gets closer and closer to a particular y value, then, and also, so notice there's an and here, this and, the values of the function can be made arbitrarily close to this value, this L value, which is a y value, by taking values close enough to c but not equal to c. And what that means is, if arbitrarily close means as close as you might want me to get. So if you wanted me to get, back in that last example we talked about, if you wanted me to get as close to 4, like within 1/1000th of 4, and you challenge me to find a value that will get me as close to 4, but not equal to 4, but within 0.001 of 4, I can find it. I'll just have to choose a value, obviously, very, very close to 2 from either side. So this definition you have written down, and we'll look at the parts of it as we proceed in this lesson. So to look at an additional example 1, we're going to look at, and I'll write this down on this page here. Let's assume that our function is similar to the one that's in the book, but instead of sine of x over x, we're going to make it sine of 3x over x. And of course, we want to be sure we're in the radian mode of our calculator. What we want to find now is the limit of this function as x approaches 0. And that's how we read it. The limit of f of x as x approaches 0. This notation is underneath this little symbol for limit, but we read it as limit of f of x as x approaches 0. So let me just reduce that for a moment and take a look at, if we were going to graph sine of 3x over x in the window negative 2 pi to 2 pi in x and negative 2 to 4, this is what the graph would look like. So you can see it kind of resembles the sine function, but because we're dividing by x, we know that the domain does not consist of 0. 0 is out of the domain. So there's no value at 0. The graphing calculator does not do a nice job of showing that, as we know. So this is what the graph looks like, and it appears that as we get closer and closer to 0 from the right, we're getting closer and closer to what looks like 3. As we get closer and closer to 0 from the left on this curve, we're getting closer and closer to 3. Notice at 0, when we make a table of values, 0, we get an error value at 0 because of the fact that it makes the denominator equal 0, and sine of 0 divided by 0 is not defined, it's indeterminate. So what we do, though, is we look at values close to 0, like negative 0.1, get even closer, negative 0.01, get even closer, negative 0.001. We can carry this as far as we want to before it gets tiring. And then from the other side, 0.1, 0.01, 0.001, notice we're getting closer and closer to 0. It appears that the y values from either direction are getting closer and closer to 3. So with the graph and with our table as an aid, we would say with confidence that the limit of f of x as x approaches 0, where f of x is equal to sine x over x, is equal to 3. Clear that page and reduce it. Additional example 2 is similar to the one in the textbook, except we're going to look at another function to which your graphing calculator will not provide any help at all. We're going to define this function as a compound function, a two-part rule, as follows. F of x equals, and as soon as you see these brackets like this, it's probably because of a two-part rule. The function is equal to 1 if x is an integer, and the second part of the rule is the function is equal to negative 2 if x is not an integer. So if we started thinking about how to draw this graph, here are our axes. We'd say, all right, well, if we're at an integer, so the value is like 0, it's 1. And at 1, it's 1. And at 2, it's 1. All these integer values, negative 1, it's 1, and so on. But if we're not at those values, then the value of the function is negative 2. So we go down here, and it looks like we don't have a value here, so I'm putting an open circle, but negative 2 in between. And we have negative 2 in between. And I'll provide a better picture of that. Let me minimize this and go to this. So this is basically our function's graph. So if we want to look at the limit of this function as x approaches, let's say in this case, negative 1. Well, let's just look at this curve and see that as you get, now we're not concerned about what happens at negative 1, but as we get closer and closer to negative 1 from either direction, it should appear to you that as we're going along here to negative 1, we're getting closer and closer to negative 2. Now remember, in the rule for our informal definition does not concern ourselves with necessarily equal to c, but as we take values close enough to C but not equal to C? Or if we want to get as very close to C as possible, is there a particular value that the function is getting closer and closer to? So as we get closer and closer to -1 from the right side and from the left side, we are getting closer and closer to -2. Now, is the value of the function at -1, -2? No, it's not. But as we get closer and closer, it is. Additional example 3 is a function that has quite a rule to it. Let's take a look at that. I'll clear this page. And our rule for this function is going to be, and you're probably welcome to try to graph this on your calculator and make sure you can graph it correctly. It's equal to the opposite of cosine squared x, cosine pi x, minus sine pi x. And we're going to try to find the limit of f of x. Notice how I write this. Limit of f of x as, and I go back here, as x approaches -1. So of course we're curious about a graph. So here's what our graph looks like. -1 is located right here. So if we look at it, it looks like it's getting closer and closer to a y value of -1. If we zoom in to this point and try different values, we can see that as we come from the right side or the left side, this is coming from the right side because our values are ever so slightly larger than -1. Here, ever so slightly smaller than -1. In both cases, the y values are very close to -1. So if we can go back to here, we would say then that the limit of this function as x approaches -1 is equal to -1. Now there are 3 cases where functions would not exist. And again, examples 4, 5, and 6 in the book illustrate each of those, but I'd like to just make sure we understand those completely. In the first case is if we have a case where a function becomes infinitely large or infinitely small as we get closer and closer to a value of c, which would be an x value from either side. And what this should get you to think about is asymptotes. A vertical asymptote, as you know, when we have graphs that have an asymptote, the graph gets closer and closer to a particular, as you get closer and closer. So let me just draw a quick one. The one in the book was 1 over x squared. If we look at -1 over x squared, then we have as x equals 0 as a vertical asymptote. So as I get closer and closer to 0 from either direction, in this case our function is taking on infinitely small values. Therefore, we say that the limit does not exist as x approaches 0. Now that doesn't mean that the function's limit doesn't exist as x approaches, say, 1 or -1 or 5, which is out here. Those limits exist. It looks like they're getting closer and closer to a particular value. But as x approaches 0, this particular value 0, as we get closer and closer to 0, there doesn't seem to be a number that we can really say that the function gets closer and closer to. So we say the function's value, the limit does not exist. Secondly, if there's no limit if a function approaches a value L on the right side but approaches another value, and that's what this notation means here. M and L are not the same, but the function approaches 1 from one direction, in this case the right, and another value from the left. So when you approach when you're approaching x from the right and left, you don't get the same value. You get m in one case, L in the other. These are 2 y values. And if they're different, then obviously we can't pick a winner. We're not in the business of picking a winner. We're going to say the function's limit does not exist. And lastly, example 6 illustrated this. It's a trigonometric function which oscillates infinitely many times between 2 numbers. So in that case, if you take a look at example 6, your graphing calculator does not really clearly convey this, but if the value of the function keeps going up between a value, and I think in the book it was between -1 and 1, infinitely many times, then the limit doesn't exist. So exercises that I'd like you to complete are here. The odd-numbered exercises you don't have to submit. Evens you do. There will be a form on the website to do that. If you have any questions, email me. Good luck.